Okay, good morning everyone. Are there any questions or concerns pertaining to what we discussed yesterday? Right, so we discussed planarity, some terminology related to planarity, and then we discussed the Jordan Curve Theorem and the related topological concepts. Okay. So just to remind you, if you have a simple closed curve,
Sir, I guess
then
you aren't sharing screen.
oh, I'm not sharing screen. Thank you. Thank you. Okay. Now I'm sharing the screen, I hope. Okay. So if you have a simple closed curve in the plane, it partitions the rest of the plane into the interior and the exterior of the curve, right? These are arcwise connected open sets, each of them, right? And sometimes you will need to refer to the closure. So closure just means you include the boundary, right? So the closure of this one, we will write as interior of C with a capital I, and likewise the closure of this one, we will write as exterior of C with a capital E. Okay? And in particular, the intersection of these two is exactly the cycle, the closed curve, simple closed curve C. Okay? And the important point to note here, one implication of this is that if you take any point in the inside, in the interior, and any point in the exterior, then any arc that joins these two will have to cross the cut, the the closed curve at least once, right? It could be more than once, but it could also be just exactly once. Okay. I'm so used to graph theoretic notions that I keep using the wrong terms. So every arc joining a point in the interior of the curve to a point in the exterior meets the curve in at least one point. Okay? You have to cross the curve in order to go from the inside to the outside. Good. So why do we care? Yeah, Shrikant has a comment. The number of times is always going to be odd. That is also correct. If you cross the curve once, you will go from the interior to the exterior. If you cross it a second time, you will come back to the interior. So in fact, it has to be an odd number of times. In fact, it must be um, an odd number of times. Okay. Good. Any other points? All right. Um, so why do we care so much about the Jordan Curve Theorem? Well, you see, if you take a planar embedding of a planar graph, in fact, let me introduce one more terminology. Rather than always saying a planar embedding of a planar graph, we will use the term plane graph. Okay? So plane graph is not the same as a planar graph. It is a planar embedding of a planar graph, obviously, because otherwise you would not have a planar embedding. Okay, so I won't keep saying planar embedding of a planar graph, I'll just say plane graph. So if you take a plane graph, let's say G tilde. G tilde is your plane graph. And G is the underlying abstract graph, right? What we usually call as a graph. So can anyone tell me what is the connection between simple closed curves of G tilde and and between G? So what do simple closed curves in G tilde look like? I claim that there is a correspondence between the simple closed curves of G tilde and some graph theoretical concept in the graph G. Anyone? If you look at any simple closed curve in a plane graph, what does it correspond to in graph theoretic terms?
Corresponds to a cycle.
It corresponds to exactly the cycles of G. Right? And that is why this Jordan Curve Theorem is going to be really important, because as you have seen so far in graph theory, cycles are important. And cycles, the importance of cycles in planarity cannot be emphasized enough, as you will see during this module. Okay? So that is why we care about JCT. All right? Are there any questions or concerns regarding all of this? There's another point I want to make that I kind of alluded to yesterday. Anything that you can draw on the plane in a planar fashion can also be drawn on the sphere. Okay? So I won't even write down a proof of that. You can read about stereographic projections if you are not familiar with it. A graph G is embeddable on the plane if and only if I think what I mean embeddable on the plane is without crossings as a planar graph. If and only if G is embeddable on the sphere. Right? And if you think about it this way, then you can see that there is no real difference between the interior and the exterior. Whatever you draw in the interior can be flipped into the exterior and vice versa. Okay? So this implies that in reality, the interior of a curve and exterior of a curve are the same. And what do I mean by same? I will just be vague here, are in some sense isomorphic, but not isomorphic in a graph theoretic sense, in a topological sense. Okay? So in a proof, you can always say without loss of generality, assume that some point is in the interior or in the exterior. You will see that when we prove that K5 is non-planar. Okay? So I'll just say proof, read about stereographic projections. I like to make the joke that there is a reason so many humans, till today, unfortunately, think that the world is flat, the earth is flat. It's locally, of course, if you see around yourself, it looks like a plane, but well, we know that it's not a plane, right? And I think stereographic projection is one of the reasons behind that. All right, so our next goal is to prove that K5 is non-planar. Before we proceed, are there any questions or concerns? We will use the Jordan Curve Theorem. Later in this module, we will see a different proof using Euler's formula. But the advantage of this proof that we are going to see today is it tells you more about the structure of K5 that makes it non-planar. Whereas if you use Euler's formula, which we will discuss later, it focuses mostly on the number of edges. And it doesn't tell you so much about the structure of the graph K5. It just tells you there are too many edges for the graph to be planar. Okay? So that's why I really like discussing this proof, which explains what is it about K5 that really makes it non-planar.
Sir, can you scroll up a bit?
Yeah.
So, sir, here in theorem 10.4, you have written that interior of C and exterior of C there are in some sense isomorphic. So, what do you mean by isomorphic exactly?
I mean, in a topological sense, they are equivalent. So
Okay, so
let's do a proof of K5, and then I'll explain at one point what I mean.
do you want to mean that interior of C and exterior of C as subspaces of the plane they will be homeomorphic, something like that?
Yes, or in any arguments in our proofs, we don't need to consider two cases where a point is in the interior or a point is in the exterior.
Okay, okay.
Right? We will just consider one case because without loss of generality, we can just interchange the interior and the exterior.
Okay. So basically, they are in some sense topological isomorphic. Topological
Exactly.
isomorphic.
I mean topological isomorphism or equivalence. I'm not a topologist, so I'm not too sure of the terminology, but yeah, they are topologically equivalent.
Okay, okay. And also, sir, what is the proof of this theorem 10.4? And what is the proof? Theorem 10.4.
Well, you can probably just read about stereographic projections. The proof is in Bondi and Murthy. But you should be able to find it various places on the internet. So if you do a stereographic projection, you will get an embedding. So you take a planar graph embedded on the plane, right? You take a plane graph in the plane. Now you do a stereographic projection on the sphere. That's a projection that takes anything from the plane onto the sphere. And what you observe is that by doing so, you don't introduce crossings. If there were no crossings in the original drawing, then there will be no crossings in the projected drawing onto the sphere. And therefore, you will get a embedding on the sphere without crossings.
So basically, embeddable on the plane implies embeddable on the sphere without crossing. So
Exactly.
that proof is quite intuitive
Exactly. It is intuitive. Yeah.
because we can simply wrap the plane of
Yeah, exactly. It is the same reason why you can draw a map either on the sphere, on the globe, or you can just flatten it out and
yeah,
draw a map on a piece of paper.
yeah, because
So,
we can wrap a plain paper around a sphere and similarly we can unfold a spherical paper into a plain sheet. So
sure, that is the intuitive idea. To
yeah.
make it rigorous, you use stereographic projections, but that is indeed the intuitive idea.
Okay, so sir, the proof of theorem 10.4 I can found it in Bondi Murthy, right?
Yeah, Bondimurti has it. Yeah.
So in Bondi Murthy, the full proof is given there.
Yeah, it's just four lines. They basically tell you the stereographic projection and you will not create any crossings. It's basically what I told you.
Okay, okay, okay.
Yeah. Okay.
And also, sir, I have another question. So can you
Yeah.
just scroll up a bit?
Yeah.
So here, no, just oh yeah, yeah, yeah. Here, so when you are saying that G is a graph and G bar is a plane graph, so we are assuming that G is a planar graph.
Yeah. When I say plane graph, I mean a planar embedding of a planar graph.
Yeah, so that planar graph is G, right?
Right. Right.
So basically, G tilde is a planar embedding of G.
Yes.
Okay. Okay, yeah. Then simple closed curve G tilde will get cycles of G. Okay.
All right. Any other questions or concerns?
But sir, I have a question. So can
Mhm.
we just scroll up a bit again?
Yeah.
So when you are saying that simple closed curves of G tilde, why are you calling it curve? Because G tilde is also a graph. So basically, when you are taking simple closed curve in G tilde, so that will be a cycle in G tilde also.
Yeah, it depends on, yeah, you can say simple closed curves in the, because it's an embedding, I'm using the term simple closed curves.
Simple closed curves of
But you can also say cycles. There is no problem in saying cycles of G tilde because G tilde is also a plane graph. It is a graph. Yeah.
so
I
basically,
just want to explain why Jordan Curve Theorem matters.
cycles of G, cycles of G tilde, and simple closed curves G tilde, they are all of the
They are
same.
all the same. They are all
All
the
of
same in
the
some
same.
sense. Yeah. Yeah. Right?
Okay.
Okay, good. Any other questions or concerns?
So, sir, we will use Jordan Curve Theorem, right, in this proof of that
Yes,
K5 is not.
yes. So let's call
And
the
sir,
vertices V1, V2, yeah.
will we do the proof of this theorem using Euler's formula later?
Yeah,
Yes, sir.
yes, we will do it. Yeah, that's right.
Okay.
Okay, so that's K5. Okay. Now let us suppose that this is a planar graph. So let's say G is K5 and G tilde is a planar embedding of the same. So this is for the sake of contradiction. Okay. Supposing it is a planar graph and you have this planar embedding. Okay. So in this plane graph G tilde, I want you to look at the cycle, any three cycle. Let's consider any three cycle, V1, V2, V3. Back to V1. Okay. So I'm looking at this particular cycle, which is a triangle. And because it's a cycle, in the embedding, the corresponding cycle or the corresponding simple cycle will be a simple closed curve, right? So let me draw a simple closed curve, but let me draw it so that it doesn't look too complicated. Something like this, okay? There is a vertex V1, V2, and V3 here.
So, sir, basically, C tilde is the simple closed curve corresponding to cycle C, right?
That's right. You can view it as a simple closed curve. You can also view it as a cycle in the plane graph. Okay, so we will not distinguish too much between them, so long as we are not creating unnecessary confusion. Okay, so you can view it whatever way you like. Okay, so by the Jordan Curve Theorem, your rest of the plane. So let me just put a box around here. This is our plane in some sense, right? It breaks it into two parts: the interior and the exterior. Okay. Now, where is the vertex V4? V4 could be in the interior or it could be in the exterior.
Sir, I think
Yeah.
V1, V2, V3. You have written both V1 on the boundary of the cycle
Oh,
C.
sorry. Thanks. V1, this should be a V2. This should be V2. Thank you. Okay. So now where is the vertex V4? V4 could either be in the interior or it could be in the exterior. Okay. By our previous discussion, there is not really any difference between the interior and exterior. So we will assume without loss of generality that it is in the interior. Without loss of generality, assume that V4 belongs to the interior of this closed curve. Okay? All right. So let me put the vertex V4 in the interior. Now what is K5? In K5, all any two vertices are adjacent. So V4 is also connected to V1, V2 and V3, which is not a problem because we know that the interior is an arc-wise connected set. Right? So in particular, we will be able to, the edges V1, V4, V2, V4 and V3, V4, they will look like arcs joining V4 to each of the three vertices. Right? And they cannot cross each other because we have a planar embedding. Okay? So what this gives us is this gives us three regions inside the interior of the C tilde. Okay, what is each region formed by? You look at the segment of the closed curve containing V1 and V2 and not containing V3. and that segment along with the edges V1, V4 and V2, V4 will give you another closed curve, right? So consider the cycle Ci to be the region of the interior of C tilde that does not contain the vertex Vi. What do I mean? This is V3, so I will call this C3. This will be C2 and this will be C1. Okay? So we get three regions inside the interior of C tilde, right? All right. Is everybody with me so far? Right? So each region is formed by one segment of the original curve C tilde and two of the edges. And these edges in the embedding will correspond to arcs joining two vertices. Okay? Simple arcs, in fact, or simple curves, if you like. All right. Yeah, go ahead.
That the arcs joining since V1, V2, V3 for all lie in the interior of C tilde, not in the interior, since before lies in interior of C tilde, so the arcs joining before to each of these V1, V2, V3 will be entirely contained in interior of C tilde,
That's right, except for the ends. Yeah.
except for the ends. And we can also assume that these arcs are pairwise disjoint.
Yeah, they will not meet because this is a planar embedding, so they cannot cross each other
They
either.
cannot cross each other. Okay. So
Right?
basically, we are getting three regions. Okay.
Right? So we get exactly three regions, right?
So basically,
Good. Yeah,
Ci tilde is the region. Ci tilde is the region not containing Vi.
that's right. That's right.
Okay. So that's why you have labeled as C1 tilde, C tilde, C3 tilde. Okay.
Exactly. That is my labeling scheme. Yeah. Okay. Now, where is the vertex V5? Note that V5 either belongs to the exterior of C tilde or it belongs to, these are all the interiors, right? I mean, what I have written here, C1 tilde, C2 tilde, C3 tilde, these are all the interiors of these guys, right? Yeah, so in particular, for example, C3 is your cycle V1, V2, V4, back to V1. Okay? So either it belongs to the exterior of C tilde or it belongs to the interior of one of these other cycles. Interior of C1 tilde or the interior of C2 tilde or the interior of C3 tilde. Okay? So let's first deal with the second case. Supposing it belongs to one of these, then what is the problem? Supposing I draw V5 in the interior of C1 tilde. Supposing I put V5 here. What is the issue?
We cannot have V1, V5.
Exactly. Right. So if V5 belongs to the interior of C1 tilde, for example, then the edge V1, V5 crosses the boundary of C1 tilde, the cycle formed by V2, V3 and V4. You will have to cross that because V5 is in the interior and V1 is in the exterior. Right? And that would be a contradiction. So it cannot be in C1 tilde. Likewise, it can also not be in C2 tilde and C3 tilde. So the only option is, yeah, go
So
ahead.
this because if P5 belongs to say interior of some Ci tilde, then since Ci tilde doesn't contain the vertex Vi, so
Yes,
from
exactly.
V5 to Vi, from V5 to
Exactly.
Vi, if we draw a path, it must intersect boundary of Ci tilde at least
Yes,
once.
that's right.
So then we get the contradiction. Yeah.
Exactly. So this implies that
Am I right?
V5
Am I right?
has to be, that is exactly what I wrote, right? Except that you are generalizing for I wrote it for I equal to 1.
Okay. Okay.
Right?
Okay.
So V5 has to be in the exterior of C tilde, right? So let me draw this again. This is the interior of C1 tilde. So V5 has to be out here. But now what is the problem?
So
V4
the
V5
problem is from
crosses
V5 to V4.
Exactly,
C
V4,
tilde.
V5. But now this implies that V4, V5, the arc corresponding to this crosses C tilde. Contradiction. Because in a planar embedding, you just cannot have any crossings, right? Okay? So that is why K5 is non-planar. Right? So what you can do is you can draw three vertices V1, V2, V3. You can put V4 inside. You can put V5 outside. And now you just cannot join V4 and V5. So you get K5 minus one edge, but you don't get K5. Okay? Good. Are there any questions or concerns regarding this proof?
Sir, actually, in all of these cases, we will get K5 minus 1h.
Yes, in all cases, yes.
K minus 1h, but not K5.
That's right. Right, so this, I think this proof tells you a lot about the structure of K5. That is this last one edge that is messing up everything. Okay? Good. So what I want you all to do is I want you all to try on your own to get a similar proof for the fact that K33 is a non-planar graph. Okay? Using the Jordan Curve Theorem. All right? And you might ask what kind of cycle should you start with? There are two possible cycles, 4 cycle and 6 cycle. I recommend using a 4 cycle. Use a 4 cycle. Right? So in the previous proof, we started with a 3 cycle, V1, V2, V3. In the case of K33, you start with a 4 cycle and you try getting a similar argument. Okay? Good. Are there any questions at this point? If not, I want to switch to, let's see, how much time do we have? Okay. Let us talk about graph containment notions in the context of planarity. Okay. So what do I mean by graph containment? Um, so this concept appears, I mean, whether a particular mathematical object contains a smaller mathematical object, that question arises in almost every field of mathematics, right? Whether you're studying group theory, graph theory, whatever it is, you always have this notion, or you're considering vector spaces, you talk about subspaces, okay? So in the same sense, there are graph containment notions. When does a graph G contain a graph J. And what the problem here is, what do we mean by contain? Okay, so that is the general theme of this discussion. We are going to talk about some containment notions and how planarity is related to that. Okay, so yesterday we observed that if G is a planar graph, then every subgraph of G is also planar, right? And so subgraph can be thought of as a graph containment notion. Okay, in particular, if K4 is planar, then K4 contains K3, so K3 is also planar. It contains K3 as a subgraph. Okay, so subgraph is a notion that we have already studied. We studied in the context of bipartite graphs. A graph is bipartite if and only if it does not contain an odd cycle as a subgraph, right? Then we talked about subdivisions at some point. You might recall we talked about subdivisions when we were talking about non-separable graphs. So I want to talk about subdivisions again in the context of planarity. Okay. So what is subdivision? We define one operation. You have an edge E, UV, and you subdivide it. You put a new vertex W on this edge. Okay. In other words, you delete the edge E and put a new vertex W, join it to the ends of E, U and V. Okay. E could also be a loop. That's not a problem. The same thing can be applied with U equal to V. Right? So this is called subdividing an edge E. Okay. So what happens in the case of planar graphs? If I give you a planar graph, and if you subdivide an edge, what will you get?
I think it will be planar graph.
It will be another planar graph, right? Because there is no difference topologically. An edge is just an arc joining two points, and a path is also topologically an arc joining two points, right? The only difference is you have put some vertices on that, but that doesn't make any difference topologically. Okay, so if you subdivide an edge, you will just get a planar embedding of your original graph. You just do the subdivisions in the planar embedding, and now it is clear that every subdivision will also be a planar graph, right? So the observation, I think it's a proposition.
Sir, I think you gave
Yeah,
this problem in the do it yourself exercise.
that's right. That's right.
Yeah, for the last lecture.
Yeah. So a graph G is planar if and only if every subdivision of G is planar. Okay? If you take a subdivision and it is planar, you can also get the original graph. You just replace the path by a single edge, and you keep doing this until you get your original graph. Right? So there is no real difference between edges and paths when you are thinking about it from a topological point of view. Does everybody agree with me? Okay. Good. So subdivisions preserve planarity. Subgraphs also preserve planarity. Okay. So now let me ask you a question. Let's say G is a graph that has a subgraph H, and H is a subdivision of some graph J, and J is non-planar, then what can you say about the graph G?
Non-planar.
Right, exactly. If J is non-planar, this implies that H is non-planar because H is a subdivision of J, and because H is a subgraph of G, this implies that G is non-planar. Okay, so now this is an observation. Is everybody with me? Are there any questions at this point? Okay, so let's state a consequence of this. And you might ask, why should we worry about this consequence? We will see in a minute. So we know two non-planar graphs at this point. One is K5, which we proved. The other is K33, that you will be proving as a do-it-yourself exercise. So what happens if we take J to be K5 or K33 in this observation? So let's say G contains a K5 or K33 subdivision as a subgraph. Right? So what do I mean by this statement? I mean that G has a subgraph, and that subgraph is a subdivision of K5 or of K33, one of the two. Right? And then what does this imply? K5 and K33 are non-planar, so the subgraph will also be non-planar, and therefore the whole graph will be non-planar.
Sir, can you repeat once again? What do you mean by K5 or K3 subdivision as subgraph?
Right, right. So what do I mean by this statement?
Yeah, exactly.
Yeah, I mean that G has a subgraph H such that H is either a subdivision of K5 or of K33.
Okay,
Is it
so
clear?
the subgraph of G is either a subdivision or of K5 or of K33.
Right. There is some subgraph which is either a subdivision of K5 or of K33. There could be many such subgraphs, but that is not the concern. There is some subgraph like this.
Okay, sir. Okay, sir. Okay, sir. Okay, sir.
Okay? So does everybody agree with this consequence? Have we proved it? Okay, good. Why are we concerned with K5 and K33? There are lots of other non-planar graphs in the world. So why am I only focusing on K5 and K33?
Sir, I
Well,
have
that is, yeah, go ahead.
a question. So this consequence that G is non-planar will follow once we prove that K33 is non-planar.
That's right, that's right. This is assuming that K33 is non-planar, which is a do-it-yourself exercise.
And K5 is non-planar, which have
You
already
already
proved.
proved it, yeah.
You have not proved it. Okay, okay. So
Yeah.
once we prove that K33 is non-planar, so then it will follow that G is non-planar.
That's right. Yeah. Okay. So why should we care about K5 and K33? That's because in 1930, Kuratowski proved that this is if and only if. So this is Kuratowski's theorem, which is theorem 10.30 in the text. And this is from 1930. A graph is non-planar if and only if G contains either a subdivision of K5 or a subdivision of K33 as a subgraph. I meant to write subdivision here. Okay, so whenever a graph is non-planar, there has to exist a subgraph in your graph. That subgraph is either a subdivision of K5 or a subdivision of K33. Okay? Any questions or concerns? Let's look at one example. The Peterson graph is non-planar. And so by Kuratowski's theorem, there should be a K5 or a K33 subdivision in Peterson graph. I claim that the Peterson graph cannot contain a subdivision of K5. Can anybody give me a proof of that? Claim. The Peterson graph.
Then it would contain a triangle.
That is not true because it's a subdivision. So the triangle could become a cycle of length greater than 3.
Oh, okay, I see.
Sir, I think the argument will be Peterson graph cannot contain a subdivision of K5, right? We have to prove it.
Yes, prove it, yes.
So K5, first of all, K5 has exactly 10 edges.
Okay.
So if it indeed contains a subdivision of K5, then what will happen? First of all, Peterson graph can't have K5 simply
No,
as
it's a
K5.
it's a very long proof. Give me a shorter proof.
No, sir.
Give me a one-line proof.
Sir, it is actually one-line proof.
Okay,
Yes.
tell me.
So first of all, Peterson graph doesn't have K5 as an induced subgraph. So
Okay.
the only possibility is that if it has a K5 as a subdivision as a subgraph, then that subdivision must have at least 11 edges. But Peterson graph has exactly 10 edges.
I see. Peterson graph has 15 edges. Peterson graph has 10 vertices and 15 edges. Anyone else? Why is there no K5 as a subdivision?
Okay, I got the point, sir. Because Peterson graph is 3 regular.
Exactly. K5 is a vertex of degree 4. Every
Yes,
vertex is degree 4. So if you take a subdivision of K5, you will have vertices of degree 4, right? Peterson is cubic. Okay? So do it yourself, but we already discussed the proof. Okay? So it must be, if Kuratowski's theorem is true, then Peterson graph must have a subdivision of K33. So that is another exercise for you. Find a subdivision of K33 in the Peterson graph and conclude that Peterson graph is non-planar. Okay? This is the easy direction of Kuratowski's theorem. If you find a subdivision of K33, then definitely the graph will be non-planar. That is the easy direction of Kuratowski's theorem. The real difficult part that Kuratowski did is the difficult direction, which is if your graph is non-planar, it must have a subdivision of K33. So this direction is actually difficult.
Sir, I see a subdivision of K33.
Okay, good. Great. How many vertices does your subdivision contain?
Let me check 1, 2, 3, 4, 5, 6, and 8.
8. That is a bit odd to me. Are you sure? Can you check again? Because I know only of one type of subdivision which has 9 vertices. But I could be wrong. I could have missed some subdivisions. Anyways, think about it. I know that there is a subdivision containing 9 vertices. I don't know about 8 vertices. Okay? Good.
Okay,
Are there any
I
questions or concerns? Okay.
Sir, I also think that there will be subdivision containing 9 vertices.
Okay, good, good. All right. So if you have solved it, that's great. All
No,
right.
actually, the Peterson graph has a nice symmetric structure, and also K33 have a
Yes.
nice symmetric structure. So
Yes.
what
That's
you can do, we can simply take K33, and what you
Mhm.
can do, we can subdivide. So suppose K33 has two parts.
No,
In the
because I
first
don't want
part,
to
there.
know the proof right now, Ananya. I want to complete some other parts. So
Okay,
try
okay.
it and then maybe post it on Piazza. Okay? So let everybody try it as well. All right. Are there any questions or concerns? Is
Sir, I think
anything?
that the Peterson graph is non-planar. We can prove in a different way from the
That's
concept of.
fine. That's fine. We'll come to that later. Are there
No,
any questions concerning Kuratowski's theorem?
so basically, sir, the main part of Kuratowski's theorem is proving the forward direction.
Yes. We have already proved the reverse direction.
Yeah, that was a consequence. Yeah, that is not.
Yes. Yes. Okay, so the reverse direction is already proved. Here. Okay, good. All right. So that is one containment notion, subdivisions, which is really important in the context of planarity because it actually gives you an if and only if theorem. It tells you that the only reason a graph is non-planar is because it contains a subdivision of K5 or K33 as a subgraph. Okay? I will also say G has a K5 or K33 subdivision to mean that G has a subgraph H that is a subdivision of K5 or K33. Okay, so in order to simplify our life, I will often just say that it has a K5, K33 subdivision. Okay, so now I want to talk about a different notion of containment that we have also discussed one or two lectures ago, minors. Okay, let's see how much time we have. Okay, maybe I'll just take 1 or 2 minutes and then we'll continue the discussion tomorrow. So, what happens if you contract an edge? Remember, what do you do in minors? You delete edges, you delete vertices, which is basically subgraph, but there is one more operation which is contracting an edge. This is one of the most interesting operations in the context of graph minors. Okay, so what happens when we contract an edge? What happens to planarity when we contract an edge? Okay, supposing I give you an example. Let's say this is your planar graph, very standard example that we have seen before when we were studying Tut's wheel theorem, and you contract this edge. Well, what contraction really does, it basically squeezes this into a single vertex, right? But that does not change planarity, does it? You just squeeze this into a single vertex, and then all those edges will come here. Okay? So more generally, if you contract an edge and you have some planar drawing, it still gives you a planar drawing. You just squeeze it into a single vertex, and all those arcs now go all the way till that vertex.
Sir, in this case, we are dealing with planar graphs
Right.
that can have multiple edges,
Yes,
right?
that's right. That's right.
But is there connection like if a multiple edge graph is planar if and only if its corresponding simple graph is planar?
Yes. What do you think? Do you think that is
Yeah, it
true?
will be yes. It will be yes. Yeah.
Yeah, yeah, good. So that's another interesting point. Let me make a note here. Prove that a graph, or just observe that, I don't even know if you want to write a rigorous proof of this. Observe that a graph is planar if and only if the underlying simple graph of G is planar. Okay, so loops and multiple edges do not affect planarity. That is actually quite easy to see. So I'll let you observe that on your own. But the point I'm trying to make here is that contracting an edge preserves planarity. Okay, so if G is planar, then G contract an edge E is also planar for every edge of the graph. Okay, and what that implies is that all minors of a graph are planar. Because deleting an edge, deleting a vertex, they clearly preserve planarity. What is slightly more non-trivial than those two is contraction of an edge. But that also preserves planarity. If G is planar, then all minors of G are also planar. Just follows from the observation. Okay? Good. So that is another graph containment notion. And it turns out that in the case of planarity, you can get a similar theorem as Kuratowski's theorem, where instead of subdivisions, you talk about minors. Okay? And that is called Wagner's theorem. I will state it tomorrow, but I will just conclude the lecture today here. Are there any questions or concerns now? So the lecture is officially over. Feel free to leave.
Sir, is there any polynomial time algorithm to determine whether a graph is planar?
Absolutely, there is. Yes.
Okay.
If you're interested, I taught that in the first course I taught at IIT-Madras, Advanced Graph Algorithms. You can take a look at those lectures. I think it's around lecture 15, if I remember correctly. Okay, and we will, it is based, the proof I taught there, or the algorithm I taught there, is based on this concept of bridges of a cycle that we will also be discussing in this course. But we will not go into the algorithmic side of things. We will just discuss the graph theoretical aspects. So you might want to wait for another week and then you can take a look at those lectures. Any other questions or concerns?
Sir, I have so proposition 10.31 means proposition 10.31 follows directly from the observation, right? Written.
Yes, it follows directly from the observation.
Because a minor is obtained from G basically through a sequence of vertex deletion, edge deletion, and edge contraction.
Exactly. All those operations preserve planarity.
Yeah, and
Therefore,
all
the
those
minors have to be planar.
so minors are planar.
Exactly. Yeah.
And I think that this observation, so basically, yeah, so using this proposition 10.31, we can say that since K5 is a minor of Peterson graph, and
That's
K5
right.
and we have shown that K5 is not planar.
That's right.
So by proposition 10.31, we can say that then Peterson graph can also be not planar.
That's right. Yes. So you can use this proposition, and I think I gave it as an exercise yesterday. Use this to show that Peterson is non-planar.
And once we showed that Peterson graph is non-planar, then by Kuratowski's theorem we can say that it is either a K5 or a K3 subdivision.
Yes.
Means just going in the reverse direction means. So, and first of all,
That's
it cannot
right.
have a K5
That's right.
subdivision because it is three regular, so it must have a K33.
That's
It
right.
must have a K33. Means basically this is an alternative way of proving that Peterson graph has a K33 subdivision.
Yes, you can prove that, but of course Peterson is a small graph. You can just find the K33 subdivision.
Yeah.
Yeah.
That is constructive proof. If you can find a K3 subdivision, is it okay? Or
Yes.
otherwise, you can prove it in the alternative way.
Exactly.
So is my argument right in this
That's
direction?
That's correct. Yes.
Is it correct?
It is correct, yeah. In
Okay.
fact, Kuratowski's theorem immediately implies that Peterson has a K33 subdivision, right? Because it can't have a K5 subdivision, therefore
Yeah.
it must have a K33 subdivision.
Actually, sir, that claim was really nice. I could not see that it could have a K5 subdivision.
Right. You mean, yeah, the degree of the vertices, right?
Yeah, yeah, yeah.
Right.
But once you said that the argument will follow in one line, then I just
Yeah.
Sir, will you be
Yes.
taking the course Advanced Graph Algorithm next semester?
I don't think I will be taking it. I think Meghna Nasre in our department is planning to teach it next semester. I will probably be teaching another course.
Okay.
Yeah.
And may I know in when you offered that course,
Uh-huh.
was there a programming component?
No, there wasn't.
Okay.
Is that something you're interested in?
No, I thought there will be programming assignments.